Why is it that some molecules, despite having the exact same number of atoms, behave so differently when it comes to stability? Welcome to the Learning Assistant app YouTube channel. Today we're peeling back the layers of a subtle but powerful phenomenon that chemists call hyperconjugation. To understand this, let's start by looking at a carbocation, a carbon atom that's missing an electron and carries a positive charge. If we visualize this atom, notice that it has an empty p orbital, represented here as a vacant vertical lobe. It's essentially an empty room waiting for electrons to move in. By itself, this is a very high-energy, unstable state. It's electron-poor and desperate for help. But watch what happens when we attach a methyl group right next to it. This neighboring carbon is bonded to 3 hydrogens. These CH bonds are sigma bonds, strong, localized pairs of electrons. At first glance, you might think these electrons are trapped between the carbon and hydrogen, minding their own business. But chemistry is rarely that rigid. As the molecule vibrates and rotates, look closely at the alignment. When a CH sigma bond rotates into the same plane as that empty p orbital, they overlap. The electrons in the sigma bond start to spill or leak into the empty p orbital. This isn't a full covalent bond, but rather a partial sharing of electron density. It's as if the neighbor is leaning over the fence to help support the weight of the positive charge. But here is the key insight. Hyperconjugation is the stabilization that comes from delocalizing electrons from a filled sigma bond into an adjacent, empty, or partially filled orbital. It's the invisible support system of the molecular world. Let's compare two different molecules to see why this matters. On the left, we have a primary carbocation with only one neighboring carbon. On the right, we have a tertiary carbocation surrounded by 3 neighboring carbons. Notice the difference in the help available. As we count the alpha hydrogens, those hydrogens on the carbons directly attached to the positive center, the one on the right has 9 different bonds capable of this overlapping trick. The more neighbors you have, the more the charge is spread out. This is why you'll often hear hyperconjugation called no-bond resonance. If we were to draw it out, it almost looks like the bond between the carbon and hydrogen has vanished to satisfy the central carbon. While the bond doesn't actually disappear, this mental model helps us see how the electron density is redistributed to create a more relaxed, lower energy state. So the next time you're wondering why a certain chemical reaction favors one path over another, remember to look at the neighbors. Stability isn't just about the atoms directly involved in a charge. It's about the subtle, electronic cooperation happening just a bond away. In chemistry, as in life, a burden shared is a burden halved.